So a couple more problems from chapter 2. I want you to go through number 6 and number 8. And a couple of problems from chapter 3, which we're starting today, number 1 and number 2. So that'll be due on the 29th at the end of the month. And that week, it's reading week, winter break. I won't be lecturing that week, so we'll skip that lecture, those two lectures. All right, and again, don't forget to hand me your homework assignments for today. By now, I'm happy to report I received all the proposals from the people registered in this course, so all the term project proposals, and they're all very good topics. I think it's going to be very exciting to learn what you have to say about all this when we have our symposium later in the semester, toward the end of the semester. So go deep, go learn a lot, and we'll all benefit from that. So great stuff. Okay, so today we're getting started on chapter 3, which is all about hypersurfaces, and it turns out that there's lots of applications that relate to the topic of hypersurfaces. So we're going to learn all sorts of things. So the first thing that we're going to go through is, how to describe hypersurfaces. That's the first topic. Then we're going to look into how we integrate over hypersurfaces. Then we're going to look at how hypersurfaces are embedded in the four-dimensional space-time manifold. So that's going to be the topic of intrinsic and extrinsic geometries. And that opens up all sorts of things, including the formulation of the initial value problem in GR, opens up all sorts of things. I won't go into a lot of details about this, but it opens up all this work that was done in order for numerical relativists to get started in their numerical simulation. So first, when you simulate a space-time, you have to get it started. So you have to input into your numerical code initial data, and those initial data are constrained. So you have to solve, constraint equations to get valid initial data for numerical simulations. So that's something that is formulated on a hypersurface, and that's going to be a topic we'll be discussing. There are other things we could be talking about, and I haven't quite decided whether I'll go there or not, but in the book I have a few sections on junction conditions across hypersurfaces. So it's really a very rich topic of discussion. For our purposes, the main reason for me to talk about hypersurfaces is that while later I'll be talking about black holes, I'll be talking about event horizons, as I told you already. And as you know, black hole event horizons are null hypersurfaces. So we have to have that under our belt before we can talk about black holes. The added stuff on initial values and extrinsic curvature and intrinsic curvature, that's something that is also, I think, very important to cover, because that's all over the place in GR literature and beyond. So I think that's something you need to know something about. As usual, hypersurfaces are pretty easy to deal with so long as they're time-like or space-like. When they're null, all those subtleties that we saw before in the context of congruences, well, come back, because we're still talking about null things. So we'll have a lot of fun just dealing with those nice issues of null hypersurfaces. So let me just get started on this. So the first topic is really the description of hypersurfaces. How do we describe them mathematically? Then I said I will be talking about integration. Then I'll be talking about intrinsic and extrinsic geometries. Then I'll be talking about initial value problems. And then, there might be additional topics that I haven't decided whether I'll talk about or not. It's really a time constraint. I can't cover everything that the book covers. So let me start with the description of hypersurfaces. So there are two basic ways of doing that, and they're both useful and pretty much essential. So I'll just introduce this by means of an example. If we're talking about a two-sphere in a flat space, well, first of all, that's an easy thing to draw. So here's our x, y, and z axes. Here's our sphere, and it's a sphere of radius r. There are two ways that are useful in order to describe this surface in that three-dimensional surface. One is to say that we have a function phi of all the coordinates that happens to be a constant, or zero, I'll take it to be zero, on that surface. And in that case, one equation, I mean, there's some latitude, a lot of latitude, in fact, in choosing what that function is, but an easy function to choose when you're dealing with the sphere is to say that that the distance on the sphere is constant, and that's the mathematical expression for this. So that's one way, and that's a very good starting point. Another useful way that serves other purposes is to take your sphere or take your surface in general and put a grid on it and describe describe the grid mathematically. So what we would do on the sphere typically would be to set up, spherical coordinates. So we would have the lines of longitudes, the lines of latitudes. So we would set up an a theta and phi coordinate system, and we would say that the position vector on the sphere would be given by r sine theta cosine phi, r sine theta sine phi, and r cosine theta. And what I have here are basically parametric relations describing the grid on the surface of the sphere. So those are parametric equations for our surface. And of course, which parametric equations I choose will depend on what grid I put on my sphere. Here I've chosen the standard spherical grid. It could have been something else. So again, there's a lot of latitude here. So this description here involves a choice of intrinsic coordinates. And that's something I'll say a lot more about. So when we're dealing with hypersurfaces in curved space-time, we could put any coordinate system we want on that hypersurface, and they may not be, they may be simply, or they may not be simply related to the space-time coordinates we use elsewhere in the space-time. So typically we start talking about two different coordinate systems, one for the space-time as a whole, the other one for the hypersurface all by itself. And there will be a coordinate transformation. There will be a relationship between these coordinates, but it may not be a direct or very simple relationship. Now, each of those descriptions here carry their own sort of convenience, and they achieve different things. They achieve different purposes. This equation is a very good starting point to calculate the normal vector. So the normal vector is going to be, in general, proportional to the gradient of that function phi. So the function phi is equal to 0 everywhere on the surface. It doesn't change as you move within the surface, but it will change as you move off the surface. And therefore, the normal vector that takes you off the surface will be proportional to the direction in which the function phi changes. I've used that property before. If we calculate that, and we put that in component form, we get 2x, 2y, and 2z. And we know that if we want a normal vector, all we have to do is to normalize this so that the normal vector will just be x over r, y over r, z over r. And that's my normal vector that everywhere on the surface points away from the center. So if you're given that function, to get the normal vector is very easy. You just take gradient and normalize. when you're given those parametric equations, that's a very convenient starting point to get tangent vectors to the hypersurface. So the first description is good for normal. The other description is good for getting tangent vectors to the surface. So the tangent vectors are, vectors that take you, that give you displacements within the surface. And for example, I can introduce a tangent vector along the theta direction by taking the partial derivative of the displacement vector with respect to phi. Because what I mean by that is that, vary theta and consider a displacement in that direction. So that partial derivative means that I'm displacing myself along the surface in the direction of theta, and that's a vector that will be pointing tangent to those curves, theta equal constant. And this tangent vector, for example, while I just take the partial derivative, I get r cosine theta cosine phi. I get r sine theta sine phi. Sorry, cosine theta. And I get r minus r sine theta. And the other one I can define like this is a tangent vector along the phi direction, where now I say, let's consider a displacement on the surface in the direction of phi. And if I do that, then I get minus r cosine, r sine theta sine phi minus plus r sine theta cosine phi, and then 0 over here. So here we have the normal vector to the hypersurface, and here we have our tangent vectors. The normal vector is normalized, the tangent vectors are not. So when we first learned this in elementary calculus, vector calculus, we always tend to normalize our vectors, but here we don't normalize those because inner products between those vectors will give us the induced metric on the sphere. I'll come back to that in a second. But it's useful not to normalize the vectors and just consider them to be defined in this way. And when we have the normal and we have the tangent vectors, well, now we have a complete basis of vectors on the sphere, and that's very useful to do all sorts of calculations. So what we can do for the sphere in three-dimensional space, we can do for any hypersurface in four-dimensional space-time. It's exactly the same recipe. It's exactly the same concepts. It's just that, we have one more dimension to play with. So any questions about this? I think all that is pretty straightforward and simple. Okay, so let's do it in space-time. So if we have, so what's a hypersurface? Well, I should spell it out. It's a three-dimensional submanifold of your space-time manifold. So it has to have all the smoothness properties of manifolds. It have to have, it have to be differentiable. You have to be able to put coordinate systems on them. You have to be able to do coordinate transformations between different coordinate charts, all that stuff. Anyway, no need to dwell on that. So how do we describe it? Well, the first option is to give a restriction on the space-time coordinates in the form of a scalar function of the coordinates being constant here 0 on that hypersurface. So here's our hypersurface. It might be time-like, it might be space-like, it might be null, it might be a combination of all of these things. We have a coordinate space-time, a coordinate system in space-time, and here is the place where phi is equal to 0. If I move away from the surface, phi will be non-zero. If I'm staying on the surface, phi will stay equal to 0. The other option is to put a grid on that hypersurface, pick a coordinate system on the hypersurface, a system of intrinsic coordinates, and give a mathematical description of those curves. So here we put a coordinate system on the hypersurface. So we have a system of intrinsic coordinates on the hypersurface. My notation will be YA. Internal, I meant intrinsic coordinates. And I can give, a description of those curves by, giving the, the space-time coordinates, how they change as you move along the curves. And that's analogous to what we had here. We can give this parametric description. What I really meant to say is that we just describe parametrically all those curves that give us a grid on our hypersurface. So that's a parametric description. In terms of intrinsic coordinates. And again, I have some latitude in choosing the function phi. I have a lot of latitude in choosing the coordinate system y. And I can consider, all possibilities. But so basically, I'm treating this as an arbitrary coordinate system and treating that also as an arbitrary coordinate system. It doesn't matter what I pick for any given application. I would pick the best coordinate system to fit the surface, and I would try to do it in the most convenient way. All right. So this description, again, is good to get the normal. This description is good to get the tangent vectors. And when we put it all together, we have a complete basis of vectors in our spacetime. So for the time being, I'll consider only the time-like or space-like case. And then I'll return to the null case, introduce the subtleties a little bit later. So right now, let's pretend that we're dealing with space-like or time-like hypersurface. So if I want to get the normal vector, I just take the gradient of my function phi, and there, that's the most of it. The only thing I have to do on top of that is to normalize. So calculate this and then normalize. Now, typically, there's some conventions that are involved. So is the normal pointing in or out of the surface? That depends on how you choose your orientation. And that also depends on how you set up your function phi. So the way I like to think about this is that if there's an inside and an outside to the surface, I'm going to pick phi so that it increases from the inside out. So phi will be lower than 0 inside. It will be larger than 0 outside. If my surface is, is a space-like hypersurface, I would tend to pick phi so that it increases toward the future. Right, so that what I would mean, so the past would be represented by phi less than 0, the future would be represented by phi greater than 0, and what I would want to do is to, pick my n so that it, so in the space-like case, there's an inside and there's an outside. I would want my n to point outward. Again, it's convention. You don't have to do it like this, but it's good to set up a convention that that you adopt and stick with. If I so basically what I'm driving at here is that the convention I'll pick for n is that it always points in the direction of increasing phi, and that's going to be your notion of whether it's future directed or past directed, or pointing out or pointing in. So by convention, n alpha points in the direction of increasing phi, which means that n alpha times the gradient of phi is declared to be positive. All right. So now let's put those two things together, and I have to remind myself of the correct equation for this. What that gives you is n alpha being equal to epsilon times the gradient of phi, and I'll tell you what epsilon is in a second, times the normalization factor. Epsilon is the inner product of n with itself, and it's equal to -1 if the normal is time-like, which means that the surface is space-like. My standard notation for a hypersurface is sigma. So if sigma is space-like, the normal is time-like, and its norm is negative. And if the surface is time-like, then the normal is space-like, and the norm is positive. So that's the definition of epsilon, plus or minus 1, depending on which is which. And that's the normalized version of n, and you can check that the signs all work out and that this condition is satisfied. Yep.
So this concept of outward pointing and inward pointing.
Yep.
So this seems to depend very much on the coordinates that you set up.
Not really. It really depends on the function phi. So it doesn't matter in terms of which coordinates it's expressed. You know, it's really a convention whether you decide that phi will increase from the inside out or whether it'll do the opposite. So my notion of inside and outside is really tied to the direction of increase of that function.
And the other part then is can we always consistently do this such that there would always be a phi from the surface that would keep on decreasing?
Yeah, because you work locally, right? When you work locally, you can always invent a function that locally will have this property of being increasing across the surface. There's certainly no guarantee that it won't have weird behavior somewhere far away from the hypersurface, but as long as you're sticking to the neighborhood of that surface, and in fact, most of the time will be on the hypersurface, sometimes a little bit around it, then there's really no obstacle in doing that. Of course, if you have pathological spacetimes, like spacetimes with parts removed or singularities and things like that, then while you may not be able to have that everywhere, but for most applications, there's really no obstacle in doing anything like that. All right. So basically, so the weird thing is that when the hypersurface is space-like, we pick up a negative sign here for n with the lower index. And when you convert that to an upper index, well, you pick up the minus sign from the metric, and that tells you that n with the upper index will be future-directed if your function phi increases toward the future. So those signs, as you switch from time-like and space-like, are always confusing. I always have to remind myself that this is how it goes, and I have to stick to the convention, because if I start picking up another convention, I get confused even more. And later on, we'll introduce even more ways to be confused when we consider closed hypersurfaces that may have, well, a future part and a past part, and then we'll have to consider what is the out. So we'll come to that. You had a question? Nothing. All right. So far so good. Okay, so now we have our unit normal. We can also get our tangent vectors. And in the same way we had them for the sphere, the tangent vectors are basically just partial derivatives of the space-time coordinates with respect to the intrinsic coordinates, so that basically we're producing displacements along each line of constant, y. So we can go along y1, we can go along y2, we can go along y3, and all of those vectors here are tangent vectors to those, displacements that are aligned with the grid that we put on the hypersurface. And once we have the tangent vectors and we have the normal, then we have a complete basis, and that's typically what we need to do our work. Okay. Well, the first question that tends to arise when you're given a hypersurface in space-time is, well, what is the metric on the hypersurface? So we have a metric in the whole of space-time, but we can consider displacements that are entirely on the hypersurface, and there's going to be a metric that applies to those displacements that will, do the job of a metric, which is to convert displacements in coordinates y into space-time intervals, right? So if we consider displacements on sigma, well, I start from the general expression where my displacements are not constrained. And then I say, okay, but I will pick displacements that are confined to the hypersurface, which means that those guys here are going to be related to displacements in the y-a directions. So the restriction comes here, the restriction to the hypersurface comes here, where I say that I only pick up a displacement in the spacetime coordinates because I'm going along, the intrinsic directions of the hypersurface. So I'm writing the first differential in this way, and I'm writing the second differential in the same way. And when I have that, while I recognize that these guys here are just what I meant by the tangent vectors previously, so I have these guys, and what's left over are the coordinate displacements themselves. And what I see in the bracket is the thing that converts a coordinate displacement into a space-time interval on the hypersurface. And that thing has to be the metric on the hypersurface, and that's what I'll call the induced metric on the hypersurface. So this is the induced metric, induced from the space-time metric. In fancy language, we would be talking about the pullback of the metric onto the hypersurface. So that's the induced metric on the hypersurface, inherited from the space-time metric, which of course rules everything, including displacements, away from the hypersurface. And the notation I'll introduce for this is HAB. So HAB, the induced metric, is simply the whole set of inner products between all my tangent vectors. So if you're given the metric in space-time and you're given the hypersurface, then all you need to do to get its metric is to choose a coordinate system, and then you calculate all those inner products and you have your induced metric. Question?
If we go back to board, there's the sign of epsilon, how sure is it
Consistent with?
the inequality above the box equation?
That one over here. Okay, let's test that. So the claim is that, so we have n alpha being equal to epsilon grad phi divided by the normalization condition, and then I'm claiming that n alpha grad alpha is going to be epsilon times, well, that divided by the same thing inside the. So if we're dealing with, let's do this case first. If epsilon is +1 and we're dealing with a time-like surface, then if we're dealing with a time-like surface and epsilon is +1, that means that grad phi, the norm of grad phi, is positive, right? So if the norm of grad phi is positive, then this epsilon is 1, and this is equal to its absolute value.
So the norm of the hypersurface is positive for time-like, negative for space-like?
That's right.
Okay.
Because think of the normal. So if the surface is space-like, the normal is time-like, and the norm will be negative. Right? So if we have that case over here of a space-like surface and a negative norm normal, then this is -1, but then this is going to be minus its absolute value because this is negative, and we still get the right sign. So are you satisfied with that? Okay. So that gives us the induced metric, and that's a useful quantity to know about. Here we have something interesting. I have two coordinate systems in my picture now. I have the global space-time coordinates, and I have the intrinsic coordinates of the hypersurface. And I'll be very careful at distinguishing, for example, tensors that are space-time tensors versus tensors that are hypersurface tensors. In the book, I was almost, clear to the point of being pedantic about these things, but I think these distinctions are pretty important. When I look at something like this, well, I see indices, and I say, well, it must be a tensor if it has indices. But a tensor relative to what? This is going to be a tensor relative to coordinate transformations of the intrinsic coordinates. But it's a bunch of scalars if you look at transformations of the space-time coordinates. And the distinction is important. So these are scalars relative to transformations of the space-time coordinates, but it's a tensor relative to transformations of the intrinsic coordinates. And this you can recognize because if you remember the steps and you remember what these things stand for, what you find if you perform a coordinate transformation is that, well, so if you perform a transformation of the space-time coordinates, you'll find that the Latin indices will take care of themselves, and all of those quantities here will transform as scalars under a change of space-time coordinates. But if you change the intrinsic coordinates and leave those guys alone, and you have the freedom to do that, then you find that, well, the Latin indices here will take care of themselves, and you'll find that these guys do transform as a tensor in that sense under transformations of intrinsic coordinates. So we'll have a bunch of quantities like this in this discussion of hypersurfaces, which have this sort of dual characterization. So if you look at them from a point of view of space-time, they might be vectors or scalars or tensors, but they might be something else from the point of view of the intrinsic coordinates. So I think it's important to distinguish what are tensors on a hypersurface versus what are tensors globally and vice versa. All right. In most discussions of hypersurfaces, the distinction tends to be subtle, or either it's spelled out or it's not spelled out. Well, I think it's good to be clear about this. And as I told you, I think in the book I've been, very careful at trying to be clear about the distinction between these things. And these guys here, those tangent vectors, are really, the key to do the, the translation between hypersurface quantities and space-time quantities. Okay, so now we have all the vectors we need to have a complete basis. So we have a basis of vectors. We have the normal, and then we have the three tangent vectors. And to have a basis is sometimes very useful. You can decompose all sorts of things along the basis, and that's sometimes a very convenient way of doing calculations. So one thing you can do, for example, okay, I want to do this. So what I can do on the hypersurface is decompose the metric into, a piece along the surface, away from the surface. So that we've seen before in the context of congruences. but it's the same thing here. I can decompose the metric into a piece that's normal to the hypersurface and a piece that's completely tangent to the hypersurface. So that we've seen before. And of course, the sign here is important because the the sign in front here has to be consistent. So for example, if I take the inner product of n with itself, I get that. This piece here, of course, is orthogonal to n, so I get rid of it. So the point is that here we have an epsilon that comes from each quantity, so epsilon squared is 0, but I still needed this epsilon to guarantee that this is really as it should be, epsilon. So the decomposition of the metric into a normal part and a tangent part involves that factor of epsilon, so you have to remember to put it in depending on which case. Question?
Running it that way makes it seem like H alpha beta should be X now.
Yep. So what I need to work out now is the relationship between this guy and this. Right. Well, they're close.
Yeah.
But the point here is that I'm introducing it just, in this case, I'm introducing this just as something that's orthogonal to the normal direction. But yeah, so I haven't told you what the relationship is with this guy over here, but it's pretty clear that I'm dealing with a tensor in space-time as opposed to these guys, which are not, which are just a bunch of scalars in space-time. Because this is tangent to the hypersurface, there must be a decomposition of this in those directions. And the best way to write this is to say that this guy with the indices up has to be some coefficients that multiply the tangent vectors. So let me be more clear about this. That's a true equation. But what I need to, so what I want to point out, so the only thing that I want, so the starting point of my argument here is that I have an object that I know is purely tangent to the hypersurface. And because I have a basis of tangent vectors on the hypersurface, I can decompose that object into those directions. So there's going to be some quantity, I'll call it, I don't know, AB, such that I have a decomposition of my tensor into purely tangent directions. And what I want to show is that AAB is the matrix inverse to that guy over here. It's really the inverse intrinsic metric on the hypersurface. So the claim is that AAB is the same thing as HAB, and to prove this, you have to do a calculation. And the definition of HAB is that if I multiply it by the original HBC, I get the identity matrix back. So this is really the inverse intrinsic metric. So let's see if I can prove this. I didn't plan to attack it this way, but well, it's good to put yourself in danger sometimes. So let's see how it goes. Okay. I want to calculate an inner product between two tangent vectors, and just to be sure that I want to calculate an inner product between two of those tangent vectors. And just to make sure that I don't confuse indices, I'll call them M and M. And that should be equal to, well, because that's how we define these things, to HMN. All right. Instead of the metric in this form, I'll use this form. And I'll kill this term because each tangent vector is orthogonal to the normal vector. All right. Now, I'll incorporate this decomposition over here. So now we have AB that multiplies EM alpha, EN beta. And now we see what's going to happen. We have AAB that multiplies the inner product between EA and EM. And after that, we have the inner product between EB and EN. So this, by definition, is HAM. And this, by definition, is HBM. So what do we have? We have the equation that HMN is whatever that AB is, multiplying AAM and multiplying HBN. And in order for that to be consistent, that has to be equal to this. And that's the statement that A, whatever it was, has to be the inverse to HAB. So bottom line, what I have is a decomposition of H alpha beta in terms of HAB, the inverse to my induced metric on the hypersurface. Is that all clear? Okay. So the main message I'm trying to convey here is that we have a basis of vectors. We can decompose all sorts of things, vectors and tensors, in that basis. And what I've introduced here is a decomposition of the metric in all those directions. And if I want to put it all together, I can summarize all of this by saying that it's convenient to write it in the form of the inverse metric. The inverse metric will have a component along n and a component along the transverse directions, the tangent directions, and H alpha beta is something that can be decomposed into the tangent directions this way, and this HAB has the property of being the inverse to the induced metric on the hypersurface. So that kind of decomposition right here, where you say, well, you know, something that plays the role of the identity matrix being decomposed into other things, it's called a completeness relation. So it's analogous to completeness relations you would have in quantum mechanics, for example, or in other contexts. So that's, you know, so it's basically a decomposition of, you know, the metric into orthogonal directions, and it's a very useful thing to play with in calculations. It's called the completeness relation for the metric. All right, so any questions or remaining mysteries? Okay, so at this point, we're still talking about the description of hypersurfaces, and all the while I've been focusing on the time-like or space-like case. And here it's easy to do them all at once. The only nuisance is that you have to introduce an epsilon and keep track of what it stands for. And one thing that always confuses me is I can never remember whether I chose epsilon to be -1 when the normal is time-like or when the surface is time-like. I always have to go back and check what my convention was. So we just have to remember that epsilon is negative when the normal is time-like, which means that the surface itself is space-like. So, I can, predict that I will be confused about this at some point in this course. So, that's a fact of life. So that's the only nuisance, right? So apart from that, I think all of this is very straightforward. When we're dealing with a null surface, and that's what I'll do now, when we're dealing with a null surface, well, all the subtleties that we have learned to appreciate and love about the null case, come to us again, and I want to go into that now. Well, a lot of what I've done carries over, so that's the good news. One thing that doesn't carry over is the notion of a unit normal. So that we have to give up. And it doesn't work because, I needed to be able to divide by this in the time-like or space-like case to define a unit normal, but in the null case, that will turn out to be 0, of course. And that means I can't divide by that. So I have to deal with a normal that's not going to be normalized to anything. And in fact, the normalization of the normal vector in the null case is very much arbitrary. So that's one source of subtlety that arises. The other source of subtlety that's also the most fun is the fact that, well, as we saw before, the normal is also tangent, right? The normal being orthogonal to itself will be also tangent to the surface, so that those two distinct notions become coincident, and that always introduces a lot of subtlety into the description. So let's do that. Let's do so we're going to have to amend one major thing. We'll be able to import all sorts of other things that we've done already. So let's do the null case. Well, in the null case, so we still have a description in terms of a restriction on the on the coordinates, and we still have a description in terms of parametric relations, so that we can still do. In the null case. The main distinction now is that this is now a null vector, which means that we cannot obtain a unit normal. In fact, the normal that I would get from this is guaranteed to be a null vector. So what I'll do is to say, well, the normalization of the normal vector is just going to be whatever is inherited from the choice of that function. So there's latitude in choosing which function will describe the hypersurface. I'll just pick one, and I'll live with whatever normalization for the null vector it gives me. What I'm saying is that the normal in this case is going to be a null vector. I'll call it k to distinguish it, and it's just going to be by convention minus the gradient of phi. Here I'm assuming that phi increases toward the future, and this minus sign will also produce a vector k that points toward the future. So phi increases toward the future. And k, therefore, is future pointing. So that fixes the normalization, and of course we still have the statement that k is a null vector. And the other thing that we get from all of this is the fact that, well, k is not just normal to the hypersurface, k is also tangent to those hypersurfaces, to this hypersurface. So again, we have a vector that's both normal and tangent to a hypersurface. So if I draw a picture, so here's our null surface. I'll still call it sigma. It's still described by phi being equal to 0. We have a vector k that doesn't point out of the surface anymore, it just points within the surface. And it's going to be everywhere tangent to the surface, and I can't say this often enough, at the same time as being normal to the surface. If it's tangent to the surface, and we remember that vectors are always to be associated with curves, and vectors are always to be thought of as being normal, tangent to curves, I should say, what we have to accept here is that given this vector field on the hypersurface, it will come with a whole bunch of null curves that I can use to at least partially set up a grid on my hypersurface. So k being null and being tangent to the hypersurface, we know that it's going to be tangent to a whole bunch of null curves on that hypersurface. And I'll prove in a second that those curves are more than just curves, they're actually null geodesics. So what we're given when we're given a hypersurface is not just a hypersurface, a null hypersurface. We're given a hypersurface, and we're given automatically with it a congruence of null geodesics that run on the surface. And automatically, that congruence of null geodesics is going to be surface forming or hypersurface orthogonal in the sense that we understood it last week. So these curves, these geodesics, they form a congruence of hypersurface orthogonal. Null geodesics. And the name that tends to be used for those null geodesics on the surface is generators. So those are the null geodesics that, in a sense, trace the surface, they generate the surface. So we call them the null generators of the surface. I haven't proved they're geodesics yet. That will come in just a second. I need to set things up a little bit more before we get to that. But that's a very interesting property because it means that, to have a null surface, a null hypersurface in space-time is very constraining. So, you just don't get a null surface, you get everything along with it, including this network of null geodesics. And it turns out that in terms of, space-time structure, this is very rich. There's a lot of stuff going on a null hypersurface. Okay. Something I like to do, and you don't have to do it, but I like to do it. I'm already given this network of curves on the hypersurface, and I've already told you that I can use this as a way of setting up at least part of my grid on the hypersurface. I still haven't said anything about those intrinsic coordinates, but it turns out to be very convenient, at least for conceptual purposes, to adapt the intrinsic coordinates to this network of curves. And to basically build the grid on top of this, not try to do something different from this, but try to let the network of curves be a guide in setting up a useful grid. You don't have to do that. You could choose to discard this and set up whatever grid you want on that null surface, and that's perfectly valid. We do have a formalism that allows for arbitrary coordinate, intrinsic coordinate, an arbitrary coordinate system on the hypersurface. But a lot of what I do when I talk about null surfaces, and certainly a lot of what I do in the book, is to take advantage that we're given this and set up a coordinate system that's adapted to that. As I said, that pick a coordinate system that uses this network of curves as a guide to set up the coordinate system. And that turns out to be very simple, very convenient. It turns out to simplify all sorts of things when you work with that. And I think it really clarifies a lot of the subtleties associated with the null case. So that's what I'll do here. So we'll pick intrinsic coordinates YA that, the way I like to phrase it, that are adapted to the network of null curves. So far I don't call them geodesics. We don't know that yet, but we'll call them geodesics in a second. What I mean by that is that I'll pick one of my coordinates, y1. I'll pick that to be whatever parameter runs along the geodesic, and I'll call that lambda. So this is the running parameter on each curve. And the remaining two coordinates, I'll define them to be constant on each of the null curves. So here I got rid of one dimension, so my surface really looks two-dimensional. I have a coordinate that runs this way, and then I'll pick a coordinate that runs that way with the property that that coordinate would be constant along each one of those curves. So I can use that as a label for each curve. So we've played with those ideas before when I talked about a network of curves, and cross curves and so on. And then, of course, if I had the other dimension, there would be, the other transverse direction, the other tangent direction, and I would pick a coordinate, going along that way that would also have the property of being constant along each curve. So the remaining two, I'll change the notation here just to specialize it. I'll call them theta2 and theta3, and I'll just condense the notation into theta a this way. Those coordinates, I still have some latitude here, but those coordinates will be such that there are constant labels on each of the null curve. Those are selected to be constant on each null curve. And that's what I mean by an adapted coordinate system. We picked a coordinate system so that the description of this network of curves ends up being very simple, because in that coordinate description, theta a is constant on each curve. The only thing that changes on that curve is lambda. And as you vary lambda, you move along one curve. As you vary the labels, you move across curves, and you have a very clear geometric picture of what's going on and what the coordinate system means on that hypersurface. So lambda runs this way, and theta a runs across generator, and theta a is constant along each curve. So that's a very good coordinate system, and I'll just summarize this by saying that my YAs are going to be basically broken up into a parameter along the curve and then two constant labels on each curve. Okay. Let's look at E alpha 1. E alpha 1 is the derivative of my space-time coordinates with respect to y1 as I go on the hypersurface, which now we've agreed is a derivative of x alpha in the direction of lambda, keeping the other intrinsic coordinates constant. What's that direction? It's k. So lambda, of course, is selected to fit k. So if k is tangent to the curve and lambda is increasing along the curve, it's got to be true that those derivatives here give us k. So how did I pick lambda? Well, I picked lambda such that this equation is true. So that's really a definition for lambda, how it varies along the curve. It varies along the curve to make sure the partial derivatives of coordinates with respect to lambda give me k. So this is really a definition of lambda. And it confirms the fact that one of my tangent vectors is the vector k, which was also the normal vector. The other guys keeping lambda fixed are just my other tangent vectors. And one property that I will impose, again, that has to do with the latitude that I can pick various labels and various things that will be constant on curves. One property that I will impose is that these guys will be orthogonal to k. So that's basically, it's a restriction, the freedom to choose the remaining two angular, I say angular coordinates, but the remaining two intrinsic coordinates on the hypersurface. Oops.
Does that just follow from the fact that we have said that theta A is constant along each curve? Or is that a different statement?
No, it's the same statement. Is it the same statement? No, so here, let's see. Okay, right, yeah, I'm having a little doubt here. And I'm not sure, I don't quite remember whether this is something that's just guaranteed by the construction, because, I mean, we know that all those vectors, all those vectors here are supposed to be tangent to the hypersurface, so they're defined to be tangent to the hypersurface, which means that they all have to be orthogonal to the normal vector. K is still included because it's normal to itself, but those guys have to be orthogonal to K just by virtue of the construction. So I think that just comes for free. But I'm not sure to what extent K being null doesn't mess this up a little bit. But anyway, I think I can always impose this, and it's really a restriction that when I move across curves, I really move across curves. I don't also move along the curve in a way like this. So, so if I pick a value for theta here, I'm going to move across the curve and select this value to be the same, at this point here to have the same value of theta. Lambda. So if I pick the value of lambda over here, I move across the curve, and I'm going to pick this point to have the same value of lambda, and that's the construction I really want to do. What I don't, so it doesn't make a difference, because if I call this, so never mind. So we'll just accept this, and someday I'll think a little bit more deeply as to whether this is fully guaranteed or is whether it's something we need to impose on top. Okay, so the good news coming out of all this is that if we adopt this as a good system of intrinsic coordinates on a hypersurface, we don't have to, but let me sell it to you. I find it very convenient, and I've done a lot of work along those lines where I pick a coordinate system like this to work on null hypersurfaces, for example, black hole event horizons. If you adopt this, then it turns out that all the subtleties, all the confusing things that happen in a null case, basically it's all taken care of. So once you've done this, you really don't have to. So it basically saves you from being confused at all sorts of other places down the road, because this basically fixes everything to such an extent that you don't really have to worry about subtleties. You don't have to worry about a lot of a lot of things when you work with null hypersurfaces, it basically protects you from further confusion. So if only for that, I find that this is a really good idea to adopt this. But I keep stressing that, well, this is a choice that I make. I take advantage of this network of curves that's given to us, and I wouldn't have to make this choice if I didn't want to. I just like to make this choice, and I find it saves me a lot of confusion when I work with these things. So, well, you're stuck with me for a while, so we're going to do this in this course. But an advice to you would be to, if you ever find yourself working on null hypersurfaces, this is really a very good way to do things. Okay, so we have a basis of vectors, so we can decompose things in that basis. So I'll do that, and I'll talk about the metric decomposition before I clean up the point about those curves being geodesics. You have a question?
Yeah, are the EAs null?
No, these guys are space-like. They're fully space-like because after you've basically eliminated this null direction from the hypersurface, the only thing that you have as remaining directions is that space-like transverse space that we talked about before.
So that's kind of different from the space-like and time-like surfaces, because if you think of like a space-like surface, all the directions are going to be space-like in that surface.
Yeah.
But here we just have one direction being null.
That's right. That's right. But even in the time-like case, if you have a time-like surface, you're going to have one direction time-like.
Well, but
the other two space-like.
The normal, which isn't in the surface in that case, which is
yeah. So here, so it's a bit weird because you still have that null direction.
Yeah.
But the remaining directions after you remove that one are the orthogonal space. What I used to call the transverse directions last week, and those are space-like.
Can they be time-like or just space-like?
No, they're space-like. Okay. They're guaranteed to be space-like. It's good to point out. Okay, so we have, as I said, we have a vector basis. We can use that to decompose vectors. So I'll do that first, and I'll use this tool to prove that we're dealing with geodesics after all. So you all have this information. Okay, so if I want to prove that those curves are geodesics, I have to say something about the acceleration associated with that tangent vector. So let me construct a vector A alpha that's defined to be the covariant acceleration of k in the direction of k. The covariant acceleration of k. And I can prove that the curve is a geodesic if either this is 0 or if that is proportional to k itself. So that would be the generalized version of the geodesic equation. So let's see what happens to that vector. So that's a vector that's defined on the hypersurface. As I calculate the rate of change of k along k, I'm moving entirely on the hypersurface. So the vector that I'm defining, as the acceleration vector, so this derivative basically involves only information that is contained on the hypersurface. I'm really taking derivatives as I follow the flow of those curves on the hypersurface. What I was trying to say is that, well, that vector that I'm calculating here, though, we cannot sorry. What I'm trying to say is that this vector will have components tangent to the hypersurface, but it will also have components normal to the hypersurface, or components that go away from the hypersurface. And we're going to see it by direct calculation. So what I really was trying to say, and what I should have said first, is that what I have so far is only a partial basis. I need another vector to complete that basis. And the reason for that is that, well, before in the timeline case, I had the normal and the three tangent vectors as all, distinct vectors. But now, because of k being, orthogonal to itself, I find that one of my e vectors coincides with k. So, I thought I had 4 vectors, but I only have 3. And if I want a full basis, I need a fourth one. So before I go back to this discussion, let me introduce the fourth vector. That's going to be basically another null vector that's going to be pointing away from the surface. And we've seen that null vector before. It comes back here in a slightly different context, but it's basically the other null vector that we can introduce that's going to be pointing along the, the other null direction that points out of the surface. So let's drop this for the time being. I missed a step. So what I'm saying is that we have to complete the vectorial basis, which so far involves only k and 2 space-like vectors with a fourth vector. And here we have some choice. But because we're already given a null vector in this whole business, I find it convenient to pick the fourth vector to be a second null vector that's going to have the same properties that, that we've encountered before. So n is going to be our selected fourth member of the basis, and it's going to have the property of being null. It's going to have the property of being normalized with k in the usual way. And it will have the further property of being orthogonal to all the other vectors that are tangent to the hypersurface. That set of conditions produces a unique solution. So that's a difference with respect to the context we had last week, where we were given a congruence and we had to pick arbitrarily a second null direction. Here we have something much more rigid because we have an entire hypersurface. And we have an entire hypersurface, and we've already selected our basis vectors within the hypersurface, and we want our n vector to be orthogonal to all of those things. So, and so unlike the case where we had before, where n was not unique and we had the freedom to rotate n and so on, here, in fact, once we've selected this and selected that, we have enough conditions to pick n uniquely. So that's a slight difference, but other than that, n plays exactly the same role. Okay, so now we have a full, a full basis for our null hypersurface. We have 3 vectors that lie within the hypersurface, and we have this auxiliary null direction that points away from the hypersurface, also in a null direction. Okay, now go back to my discussion. And let me try to say again what I was really trying to say. The vector k is defined everywhere on the hypersurface, and it's not defined anywhere else. So if you were asking me to calculate the derivative of k going away from the hypersurface, I wouldn't know what to do, because k is defined only on the hypersurface. It's not defined anywhere else. But if you ask me to calculate the derivative of k anywhere along the hypersurface, moving within the surface, either in the direction of the curves or in the direction across the curves, then I know what to do, because k is defined everywhere on the hypersurface, and I know how to calculate those derivatives. So that vector on the right-hand side involves information that's contained purely within the hypersurface. So I know how to carry out those operations. That doesn't guarantee that the vector I'm constructing will necessarily be tangent to the hypersurface. And I could not assume this, because if I did, I would be wrong. So what I'm going to do is to use my basis to decompose A into all of it could be, and we're going to figure out what its various components are. So what I'm saying is that this is a vector that can be decomposed in the basis, and it's going to have a component along k. I'm going to call that component kappa. It's going to have some other component, this one I'll call, I don't know, a, along n. Sorry, I'll leave n for the last one. It's going to have a bunch of components. Let me call them a along the transverse directions. And it could also have a component along n, because I cannot guarantee, and I would not guarantee, that sorry, it would be dangerous to assume that this component doesn't exist, because a vector like this has a chance of having a normal and tangential components. Okay, it's good to remember that k alpha is defined as the gradient of a scalar function. So, okay, so how do we calculate these components? Well, the first thing you could do is to calculate the inner product. And according to the decomposition, the inner product of k and k is 0, the inner product of k and e is 0, and the inner product of k and n is -1. So the component b, whatever it is, will turn out to be just the component of the acceleration vector along k. Here it's confusing because I'm talking about a component along n, but it really turns out to be a component along k. So that's the other weird thing that has to do with null vectors. There's no good way of saving yourself from confusion from that. So I won't even try. But so I'm really talking about a component along k that gives me this coefficient along n. Deal with that. Okay, so what is b? Minus b then is going to be k alpha differentiated with respect to b, and then we multiply by k, and we multiply again by k. This is the same thing as 1/2 k alpha differentiated in k. And that's 0 everywhere along the curves. So b, after all, despite all my warnings, b turns out to be 0. The point is that you have to prove that it's 0. If you were to just assume it, you might run into some danger. Okay. Okay, so that's the first thing we did. The second thing we can do is to take an inner product of a. I have too many a's here. I shouldn't have called this AA, but anyway, doesn't matter. I can take inner products between a and my two transverse vectors. And according to the decomposition, well, the inner product of e and k is still 0, but these guys are not 0. So I get a times the inner product of e. Oh, sorry, I have too many equal indices here. Let me call this e. So here I have eb multiplying ea. Those guys are not 0. And I'm going to invent a notation for this in just a little bit later. But let me just point out that they're not 0. Whereas the stuff on the left-hand side is equal to k alpha differentiated with respect to beta. And then we have eb and k beta. Okay. All right, now I don't know what to do with this. Ah, I know what to do with it. Let me do a side calculation. K alpha differentiated with respect to beta is the same thing as phi differentiated twice. The point is that this is something which is symmetric under an exchange of two indices because two covariant derivatives acting on a scalar are interchangeable, which means that because k is equal to a gradient, we have that it satisfies this property. And that's what I needed, because I needed to change this into a k beta differentiated with respect to alpha, multiplying k beta, multiplying e beta, e alpha. And that's the same thing as a half k beta differentiated with respect to alpha in the direction of e. And again, because the vector is null everywhere on the hypersurface, this is 0. So I get rid of that. Will I get rid of the last component? Well, let's find out. The last thing I need to do here is to take the inner product of my vector in n. And now I've killed two other components, so what I get when I multiply the right-hand side by n is a -1 from the k. So kappa is going to be related to this component of my acceleration vector. So what do we have here? Well, this is equal to, again, k alpha, k beta in the direction of n alpha, k beta. I can play the same trick I used before. This is k beta differentiated with respect to alpha, k beta, and alpha. This is the same thing as 1/2 k beta differentiated in the direction of n alpha. And if I want to be even more precise, I have that. That I cannot claim is 0, because I know that grad phi is going to be 0 anywhere on the surface, that the norm of grad phi is going to be 0 anywhere on the surface. I have no way of guaranteeing that if I go off the surface in the direction of n, that this property will remain true. And in fact, there would be no reason for that property to remain true. So that derivative is not 0. No, didn't want to do that. This is not 0. Because even though this is 0 everywhere on the hypersurface, here I'm asking about how does that change as I go off the hypersurface. And I don't know. It will depend on what my function phi is. I know it describes one null hypersurface. It could be that it describes a whole stack of null hypersurfaces, in which case it would be 0. But in fact, it could, the surface phi equal constant could be side space like on the other side and null right here. In that case, that norm would not be 0 everywhere, anywhere outside of the hypersurface. And in general, I cannot guarantee that it's 0. So it's going to be 0 in some circumstances, very specific circumstances. In general, though, it's not going to be 0. Bottom line, I can't kill this term, but apart from that, I know that my acceleration vector will satisfy this equation. And that is the geodesic equation in generalized form. So whatever kappa turns out to be, we have, regardless, we have the geodesic equation. And if kappa is not 0, what we've learned from this is that lambda is not going to be an affine parameter. If kappa turns out to be 0, depending on what else is going on, away from the hypersurface, then lambda will also turn out to be an affine parameter. In general, we will be dealing with a bunch of null geodesics, which are not affinely parameterized. But sometimes we're lucky. The phi equal constant surfaces will turn out to be null everywhere, in which case we would have a foliation in terms of null surfaces. In that case, the norm of grad phi would be 0 everywhere, and in that case, kappa would be 0, and we would have a null surface generated by null geodesics, affinely parameterized. All right. Okay. Yep. So yeah.
This calculation up there, isn't there a minus sign up on the corner? K alpha beta.
Where? Sorry.
K alpha beta minus phi, the covariant derivative. On the left.
Here.
Here.
No, sorry. There were too many minus signs here. So there's one in front, and then it gets removed when I go back to K. Yep.
So this basis doesn't really let us decompose the metric though, right? We need like 2 new vectors from combinations of K and N.
We can do the metric. In fact, I think I'll just do the metric this afternoon because we're out of time for now. But yeah, so the next step, I wanted to introduce the idea of a decomposition to deal with the acceleration first, and then I'll apply the decomposition to the metric. And we're also going to have a very neat decomposition of the metric, in terms of that basis. All right. Other questions before we break for lunch? Okay, so the main message here is really to say, okay, we know that in the null case we have to face all sorts of subtleties and things like that. My claim is that if you let the null curves be a guide to set up a nice coordinate system on a hypersurface, then all of those subtleties can be basically dealt with once and for all. And after that, you can sort of go through the entire formalism without having to worry any more about those subtleties. It's been taken care of already, and I find that to be very convenient. So we'll see examples of that certainly when we proceed with this and when we start moving into integration over hypersurfaces. So that's what we'll do this afternoon. So I'll see you then.